I love your kids drawing.
Thanks, me too. I hate to erase it. Did you guys see how she spelled meadow? M-E-D-O.
Still better spelling than Jake.
So apparently a really good way to encourage kids' literacy is not to correct them, because society will correct them plenty, but to encourage them to write, just so that they feel like, sure, I'll give it a try. And so I try not to laugh when she spells stuff funny, and I was watching her write, and she got hills right, and she got trees right, because she's learned those rules.
What is that for?
She,
Birch?
yeah, I bet, oh, that's an orchard. She almost got orchard right. She got rock. She did all three of the rocks right. She misspelled river, but whatever. I think she spelled flowers right, or almost right. But then when she labeled meadow at the end, I was like, what's all the green stuff? She's all, Dad. And it says me-do, like M-E-D-O. It's so hard. You don't want to laugh at, like, being a parent's so weird. Like, when she was a baby, she barfed in my mouth. And, like, you don't want to make her feel bad for that, because, like, she doesn't have control, and they feel bad. And so, like,
you guys are forever have a special connection.
I mean, think about it. I'll bet you money, all the things you're ashamed of, your parents sort of taught you to be ashamed of them. Basically, almost all of them. And so, I don't want my children to be ashamed of anything, let alone their spelling. And so I try not to, like, but it's so hard when you're a parent. You just can't help but, like, every now and then, like, dang it. Like, we give our children complexes.
She barfed
in public. In front of my class, I should add. My daughter brings her to school, and I'm like, hey, everybody, look, you know, your baby. And I had been talking, it was my first child, and so my students that year, like, it was just baby talk nonstop. First it was pregnancy talk, then it was delivery talk, and then it was baby talk. And so that class, like, they'll, whenever I see those kids, I always ask me about Ona, because that was such a big part of our classroom life. So my wife brings her to school, and I'm like, look, everybody, that's my baby. And somebody was like, do you throw her up in the air or something? I was like, oh, she loves it. And my wife's like, she just ate, no! And I'm like, what? And right as I catch her, she goes, whoa. So it was like this. And I was like smiling at her, trying to make eye contact, you know, like, all goo goo gaga. So I was laughing, you know, with my mouth, laughing. And she goes, what? And like, it was straight, like, from right here. It was like,
That's like reverse Mama Birdie.
I was like, I passed her to my wife, and then I rinsed out my mouth. What else am I going to do? Like,
Not the end of
keep it. I put it in a jar for later.
It's a snack.
I munched because I was kind of hungry. Good-spirited. All right.
You should have played it off like it was totally normal.
Yeah.
Thanks.
So you want to do this?
Hint of broccoli.
Thank you.
Yeah. Spit it.
I shook her and I yelled, "Bad baby!" But that's not okay? Alright, I'm sorry, but we're getting dragged down. We're getting dragged down here. Did we do the current one yesterday?
No.
So I'm going to need a volunteer, please. One volunteer now, please. One person, come up.
Take initiative.
Come on, volunteer.
Jackets around the waist.
Anybody else? I'm just kidding. All right.
So not kidding.
Okay, students, this is about to get really sciencey, so you'll want to wake up. Reminding you where we left off yesterday, and I guess you'll have to stand here for a minute. You're doing a really good job. Sit there and be handsome. Remember that this explains wind. This is what wind is. When air is moving from high pressure to low pressure, this is also known as wind, is the scientific term. If you're standing right here, the wind is blowing that way. Okay, that's what makes wind. If you're standing right here, the wind is blowing that way. If you're standing right here, the wind is blowing that way. And if you're standing right here, the wind is blowing that way. So on the surface of the Earth, on average, surface wind, except for weather, on average, surface wind goes from the north to the south here, and from the south to the north here. So I'm going to draw those next to Grand Collector. Here it comes. From 30 to 0, we have a dominant north-south arrow. Then from the 30s northward, we have a dominant south to north arrow. Everybody got that? Yeah. Coming up at the equator, there's another one that goes like this. And I want to remind you that Cristobal or Christopher Columbus was an Italian sailing under the Spanish flag. There he is, pushing out into the Atlantic from the Mediterranean. Now, if his world was only governed by what you've learned so far, the wind would have carried him south to the equator, where his boat would have stalled. Because at the equator, there's a phenomenon called the doldrums, where there's no wind. How many of you have heard about this? So when you sail around the planet, you got to find some little tricks to get across the equator. Also to get across the 30 to 60 because of the wind shift. Charles Darwin's captain experienced a problem. When they tried to leave the Galapagos, they sailed for about 1 day, and then they hit the doldrums, and they were basically stuck in place on a sailboat, unable to reach land and exit the doldrums for almost 2 months. They were just like sitting in the boat like, oh man. Apparently they had other support ships that could follow the Beagle, and so they took a little rowboat off the Beagle and they dropped an anchor as a point of reference. And after a period of 2 months, they had just kind of like not even drifted. It was right next to that rowboat. But anyway, Christopher Columbus did not die in the doldrums. He found the Americas or something. And to explain how he did that, I have brought Grand Collector to represent another force. I will do wind, make wind. Grand Collector will rotate the Earth for us. And Graham, if you're looking at that map, which way does the Earth rotate? Yes, that way. So the surface of the Earth is going to pull from me to Graham. If you don't believe me, imagine that Graham is our ray of sunlight, our little sunbeam.
Sunbeam.
And if the sun is fixed in the universe, the eastern the eastern coast of the United States will see the sun rise first, then we will see the sunrise, then they will see the sunset, then we will see the sunset. Everybody got that? So that's a good way to remember that the map spins that way, because the east sees the sun first. Yes? Come on up here, homie. Hold the paper right over here. When I say go, you're going to rotate the Earth. Now, when I say go, homie's going to rotate the Earth. And when I say go, I'm going to start the wind blowing. And I'm going to go in a straight line from top to bottom. Try to stand against the whiteboard so everybody else can see. Thank you. I'm going to go from right here to right there. I'm going to go in a straight line. Okay? Ready, set, hit the rotation of the Earth. Keep rotating the Earth. You're doing a good job. Keep going, keep going, keep going, keep going, keep going. Yeah. Okay. Thanks. You can leave. This is your treasure map for how to find the Americas leading from Spain. Just stay alive on the road. See, the funny fact is, because the planet is spinning, and because our atmosphere just has 6 wheels and the baby Jesus said so, and they are driven by an updraft at the equator, so the air is being pulled up by rising heat that's sucking down wind from north to south from 30 to 0. And so this is just because the baby Jesus said so. And this is because our planet is spinning because the baby Jesus said so. And so you get what are called, please look up, the trade currents. If our planet was a cylinder and not a sphere, if our planet was a tube, then this would go like that, because it's also spinning in the same direction. Do we agree? Everybody follow me on that? Yeah? But watch, that doesn't happen. Because there's not a lot of water up here compared to all the water down here. Look at how big the planet is at the equator. Look at relatively how much smaller it is at 30. Everybody got that? So one of these has to win. The trade counteracts this one by finishing the circle that way. Those are called westerlies because they come out of the west. There's the southern trades and the southern westerlies. The wheels spin in the same direction over here. That's why a fisherman from Mexico can find his way down to the Marshall Islands. A fluke of weather skipped him from this wheel into this wheel. So he went to the Marshall Islands. That's why we get our surf and our cold water currents from Alaska. Remember that currents are made by wind moving across water. So if you can map the wind, you map the currents. Y'all feel like you understand more about your planet? A little bit, maybe? Yeah.
Could climate change cause the wind and currents to change? Like,
not these. Not these. They will slow and accelerate these because climate change changes some of these variables. So how much rise and how much blow and how tight and which shape. Climate change will most likely, let me see if I can get this straight. Climate change will most likely make the shape of these more almondish. So I think that makes a more significant difference between dry and wet. So the in-between in the middle of these becomes more sharply defined, I believe. And someone explained this to me a few years ago, and I went, and then my brain exploded, and I can't remember what. Climate change changes some of these variables, but these are fundamentals given the volume of water in the atmosphere and the basics of water tipping point evaporation, condensation on Earth. I don't think climate change will change too much of this. Certainly not the rotational effect.
What part of the planet is like furthest away and furthest ahead in time? Like in some places it's tomorrow, some places it's yesterday. Like what?
I believe Greenwich, the city of Greenwich. Isn't that what it's called? The Greenwich line?
No, no.
What is it?
It's in England.
And that's it?
Yeah, I think it's South Korea. That's been my knowledge.
And she said so. I just go. Technically, it's the same time everywhere. We just experience it a little differently, so we call it a different number. Okay. Anybody want to talk any more about this? Because I would like to skip. No, I won't skip it. Number 14. I'm assuming that you did your homework. If not, you're not going to get this. Sedimentation is physical. Rain is physical. Rain is also chemical, like oxidation and photodissociation. In number 14, those methods that take stuff out of the atmosphere, the first two are physical, the last three are chemical. Rain is both physical and chemical, removing stuff from the atmosphere. Number 15 we did yesterday, that was our warm-up. Number 16 is part of how I will answer today's warm-up. Okay. Please notice, the warm-up says, how do we know the difference between natural and man-made climate change? And I can answer this question. First, you got to figure out how climate changes naturally. Second, you got to figure out if your understanding is enough to explain what you know about climate. So third, you got to learn more about the past climate. And fourth, you got to look at what's happening now and see if the natural explanation matches or not. I can answer this question, but it takes the rest of the period. The story begins with a Serb named Milutin Milenkovic. That's his last name. Nobody really knows his first name. Milutin. I mean, people know it, but it doesn't matter. You don't memorize. You don't need to know his first name. Milutin Milenkovic was a pretty big-time nerd. People have said he was like a mega genius. Like one of those people with like extra brain capacity that could see things that other people don't see, sort of. He was a mathematician and also an astronomer. Those things often go together because you see a lot of math in the universe. And to understand why he's so important, you have to understand a little bit of science trivia. Sorry to bore you. For a long time, early astronomers thought that the universe was roughly perfect. For a very long time, people said, look, it's a perfect circle around a perfect sphere with more perfect circles all on a perfect plane. And when people first started to explain the solar system, they said, look, perfect things moving in these perfectly defined orbital planes. And then we started to notice that the solar system is not like that. It's actually quite irregular. Some planets orbit like this, off angle. Some orbits are not round. They're skinny. Some of the planets accelerate and slow down for part of their orbits. Planets are irregular. The Earth is not round. It's actually not even oval. It's shaped like an egg. It's tubbier on the bottom.
All the water.
Yeah, exactly. It bulges like that. And Milenkovic wanted to study irregularity. That was his thing. He was like, I like weird stuff. He was into the freaky things in the universe, and he wanted to find the strange. He discovered 3 major cycles, and basically these were kind of hinted at before and sort of known, but he did the math better than anybody. He had extremely sharp pencils and many significant figures. And he noticed 3 irregularities. The shape of the orbit, the rotational shift of the axis, the shift of the rotational axis, and the wobble of the axis. the first one of those, the orbit is not round, and it's not oval. It kind of changes. Anybody ever played with a hula hoop? You know, they're kind of flexible. So imagine you squeeze the hula hoop, and it kind of gets dumpy on the edges. Then you let it go, and it goes back to being round. Then you squeeze it, and you let it go round. That's the Earth's orbit. The Earth goes, please look up, from round to stretched to round every 100,000 years. And each of those extremes has a different impact on climate. Because during the years, the sun is not at the middle of that orbit, it's off on one of these foci. So because the sun is placed at one of the foci, during the years that the planet is stretched orbit, it's technically warmer. Because it receives more sunlight than on the years that, on average, it's more away from the sun for longer periods of time. So check this out. The change in the shape of the orbit creates up and down cycles every 100,000 years from hottest to coldest to hottest in climate. Yeah.
Will that be like an ice age?
Well, let's not get ahead of ourselves. But we're going to end up answering that question, just not yet. Yeah.
Then like I see, if you squeeze it, it's maybe closer to something or other, but it's also moving farther away from the general.
Yeah, and I'm not exactly clear on which one is which. And by the way, if I'm wrong about warmer and cooler, correct me, but the point is, he found an influence of how the orbit affects climate because he measured that irregularity.
Oh.
Yeah.
Does this sun move?
Sharp pencils. I believe not, but I'm sorry that I can't answer. There are smarter people than me that have a lot more knowledge about these things. I'm just saying I trust what he says on this, and I don't really know the details. The second thing he found is not just that the shape of the orbit changes, but that the angle of the Earth's axis changes. Remember, we looked at this thing, right? I'm assuming everybody can see. See how the Earth spins on an axis that's tilted away from perpendicular? Perpendicular would be spinning like this, but it's actually spinning like that. It's at an axis. And if you measure that angle changes every 40,000 years. It gets steeper and lower, and steeper and lower. The range is 22.1 to 24.5. Today it's like 24.3. We're close to one of those extremes. And again, I don't really remember the pattern. Please don't quote me. Maybe I got it wrong. But there's a warmer and a colder extreme because one of those hits more sunlight on water. So southern hemisphere gets more sunlight intensity and there's more water down there. So the planet absorbs more light and gives off more heat. So I don't really know which one is which, but that also affects, please look up, global climate on a cycle. And finally, Milankovitch measured a third cycle. Another way that our relationship to the sun is irregular. This point, right here, wobbles around. I don't know if you guys have ever seen a quarter slowing down. Like when you spin a quarter, and it's going, and all of a sudden it starts to slow down, and it goes wobble, 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 wobble. Okay, don't freak out. Our planet is not slowing down, but that's a visual of what I mean by axial wobble. It's not because our planet's slowing down. Different reason. But our planet has an axial wobble. Now, I don't know how the dude figured this out, because all these cycles are obviously much longer than his data set, right? He collected data for like 30 years, and then he wrote a book. So it's not like he measured one of these. We haven't had telescopes for 1,000 years, let alone 100,000. But apparently, now that we have satellites and leprechauns in space, it's coming together that he was right about that. And you know, not just these. Other people have found other stuff. He wrote a book write down this number, in the 1940s, called the astronomical theory of climate change. And somehow in the 1940s, he said, look, if the planet's doing this, and the planet's doing that, and the planet's doing this, now to answer Will's question, please look up what happens on those years every now and then when this cycle is at the hottest, plus this cycle is at the hottest, plus this cycle is at the hottest. Every now and then you're going to get a really hot year. And on the opposite extreme, what happens when these are at the coldest, and this is at the coldest, and that's at the coldest? Have you guys heard about how waves pile up? Like surfers know this. If you get two swells, every now and then they'll coordinate. So you get these like massive sets coming through. When you have more swell in the water, they'll sometimes cancel out. So the gaps get kind of spotty between the swells because you just get like a couple of underwhelming sets. And then they'll pile up and you get the big mackers. Everybody can't get outside fast enough. So sound waves can cancel. You know those headphones that cancel out sound? They're making the opposite sound wave. You guys know that? Here, he said, there must be some years where a peak and a trough cancel out, so there's no change. That's just average. But on a year where the three peaks line up, that'll be a really hot year. And on a peak where the three troughs line up, that'll be a really cold year. And you know, if it's like a decade of cold years, then you might get an ice age. So he came up with what's called the astronomical theory of climate change. And since then, scientists have found a zillion more. They have found little bumps and exceptions to these, plus they have found cycles of magnetic activity, plus they found cycles of solar flares, plus they found cycles of dust in between the Earth and the Sun that affect how much light reaches us. I'm not that smart. I don't know what all these cycles are. But the bottom line is, we've added up all of those and we get one of these. Now so far, that's just us trying to understand the world. We don't know if this makes any sense until we compare our predicted past with our actual past. And so look, if your science tells you that 250 million years ago it was super hot, and then you find evidence that it was super hot 250 million years ago, then your science must be pretty good. And if your science says, I'll bet you it was cold 30 million years ago, and you find out that it was cold 30 million years ago, then you must have a pretty good understanding of science. Does that make sense to everybody? So I'd like to skip to number 18 to show you how we know our science is good. This is, how do we know about the history of temperature? Well, there's like three main ways that we know about the history of temperature. Obviously, one way is we've had thermometers for a while. So for the last like 200 years, you know, Gabe measured and Gavin measured. And we have their books. And so for the last couple hundred years, we just have records. But what about before that? What about before we had thermometers? Well, check this out. There's some people that drill holes in ice caps. You see when snow falls, it traps little bubbles of air. And when that snow freezes, you can find a beautiful woman to look at the core of ice. And you can see those little bubbles and they're little time capsules. Because that's the atmosphere from a long time ago. And we already know that temperature affects the mix of gases, the relative abundance of oxygen isotopes. the relative balance of nitrates, sulfates, carbonates, and other gases, rare gases. And we also know that there's dust in these layers. So check it out. You cut little slices. You melt them in a vacuum. And when you melt them in a vacuum, you take all the dust and you carbon date it to know how old that layer was. And then you measure all the mix of gases. And by doing some fancy magic, we can find out the temperature records. Then you compare them to ice from Greenland, and ice from the Andes, and ice from the Himalayas. And you take into account how those areas predict the global average. You also have to find out how accurate each of those regions is. There's bald spots, because when the planet gets hotter, that snow melts away, and you get no records. So technically, there are periods where we don't have information from this. But if you add all those up, you should write down this number. Ice cores have given us about 1 million years of information. And we've gotten really good data for about 650,000. Next, you can go to a place like Lake Tanganyika. It's this one. Please look up. That skinny one. Lake Tanganyika is a really, really narrow, really, really deep lake. So most lakes are like this, with a deep spot where my chest is. Lake Tanganyika is like that. It's the second deepest lake on the planet. It's just over 1 mile deep. It's really narrow. So there's not a lot of mixing of the water. Whatever falls in will settle to the bottom in perfect little layers of sediment. And it's been there for a very long time. The lake is about 10 million years old. In that sediment, you have to use a really special sort of drill bit. It's really expensive. But you can pull out cores of sediment. And you can look through the sediment to find something that tells you the history of temperature. Anybody know what that would be? Organic sediment.
Like trees and stuff that would grow in certain climates?
Yeah, pretty much. Kind of. What we're looking for, please look up, is pollen. Each species has a distinctive type of pollen. They look visually different. It's like, the different feathers come from different birds. Different pollen come from different plants. And for each of these plants, we know the temperature. So watch. If we know that palm trees like this, and oak trees like that, and wheat likes this, but orchids only like that, and ferns only like this, but daisies only like that, the only place that they could have all lived together at the same time had that very narrow range of temperature. Does that make sense to everybody? Using organic sediment like this, we've gone back about 5 million, and we'll probably get about 10 million. And then, please look up, underneath the South Pole, we've been looking at diatomic algae that's also temperature dependent, the shells of different types of snails that are also temperature dependent, and pollen. And we're hoping to go 20 to 50 million years underneath Antarctica. And look what just happened last year. I'm sorry, I'm racing to the bell. I am going to need to finish this, so please try not to interrupt if the bell rings. We, last year, have finished a new study of all this data that for at least 14,000 years can tell you the temperature of any decade down to give or take 0.2 degrees Celsius. That's extremely accurate. We can give you the planetary temperature for any decade, 14,000 years into the past, down to 0.2 of a degree Celsius. Ice cores, organic sediments from lakes, and organic sediments from the ocean. Please don't back up, it'll make noise. I'd like to finish. Here's what we know. Our understanding of astronomy matches this information in the past. It also goes way back, wherever we find ice ages and other types of evidence, like different kinds of fossils, it matches. The couple of exceptions can be explained by volcanoes and meteor strikes from the past. But look, something really funny started to happen in the last 100 years or so, especially the last 40. In the known history of temperature, it's never gotten this hot this fast. It's been hotter, it's been colder, but it's never changed this quickly. And this amount of change, not only is it an unnatural rate, but it doesn't match what's supposed to be happening if humans weren't here. Our planet was heading into one of these. We should be entering over the next 1,000 years what's called a little ice age. We should be going through a period of cooling for another couple thousand. Instead, in the last 40, we have warmed more degrees than in any 40-year period in the known history of temperature. And we can explain why that happens with science that's almost 100 years old. So I'll talk to you guys again. Sorry to rush. Bye.